Hi, my name is Heather Miller. I used to be a PhD student, but I'm not anymore. I finally finished that business. And I'm still at EPFL, but I just started this new thing along with Martin and a few other people you might know called the Scala Center. It's kind of like a new, weird, open source foundation. It's totally different than how other ones operate. But I'm actually really happy to talk about that. It has nothing to do with my talk. If anybody wants to ask questions about it during the questions or find me walking around, I'm happy to chat about what that even means. But to start, I'm just wondering how many people do Scala in here regularly? Oh, so a bunch of people. I was thinking that there's going to be a bunch of, like JavaScript people or something in here, like asking why are types a big deal? Who cares? So I hope that you don't find this talk like stuff that you might already know. Really, the goal of this talk is to try and maybe cover some of the more common areas of Scala's type system that people generally use and should use and not be afraid of. So first of all, everybody knows Scala is a statically typed language. It has it's popular or famous for having a type system that is some sort of adjective on some spectrum of negative and positive, but something about rich or complex or lots of stuff. Can we agree on that? Whether or not you think it's good or bad, it's up to you. But I argue that it's rich and that you can do lots of stuff with it, and that somehow, despite the fact that we have this ridiculously rich type system that some people are using to do amazing things. So I'm actually regularly impressed with some of the stuff that the type level people manage to do with the type system. It's still not so well explained. Just the basic stuff, somehow it's like piecemeal all over the place. I don't think that I'm going to fix that right now. I'm going to try to give people some intuition about how some things work. But I just want to reiterate that I'm only going to focus on stuff that 80% of people can sort of rapidly apply, and it's not sort of the rough edges or the advanced stuff. It's like stuff you should know to be a good Scala programmer, in my opinion. So this talk is for everybody except people who think that they're a type system expert or like to make fancy uses of the type system. I'm going to bore you to sleep. So my goal is to show you some of the basics and to cover really just a handful of topics that I think that you should know or be comfortable with in order to be sort of proficient at writing well-typed Scala programs, in my opinion. So this is what we're going to cover, and it's pretty sort of standard stuff. Just wondering on this list, who here is comfortable with type classes? Actually, have you used them before, and have you seen them around? Do you even know what a type class is? Who doesn't know what a type class is? I mean, you've heard the name, but you don't really know how it works. Okay, that's cool. I mean, we can go through kind of how this stuff works. But I'm going to cover sort of the basics. So what Scala's predefined types are, the hierarchy of things, how to create your own things that are actually types eventually, what parameterized types are, so basically generics, bounds and variance, which people tend to make use of quite a bit in Scala, and things like abstract types, existential types, and type classes. Things that I'm not going to cover are some of these fancier things like higher kind of types, path-dependent types, and some type-level programming. I was hoping to cover dotty, kind of what's new is coming in dotty, but I think that in the end I removed it because it's kind of a distraction. We can always talk about that offline if you'd like. But so let's get started. So a whirlwind tour of the Scala's type system. So Scala is a statically typed language. We have this hierarchy of stuff, and your program somewhere fits itself in the middle here. Okay. So on the top we have this common superclass called any. There's two branches, and then there's these things on the bottom, nothing and no. So at the root, any has two subclasses. So on the left, anyval, and on the right, anyref. So anyval represents basically is the common superclass of all so-called value types, and on the right, anyref is the common superclass of all of the so-called reference types. So on the left, anyval is all of the so-called primitives. So there are 9 basic sort of primitives in Scala. So byte, short, char, int, long, double, boolean, and then Scala's special thing, unit. So unit roughly corresponds to Java's void, right? So we use this in Scala when the result type of a method doesn't otherwise return anything interesting. And on the right-hand side, or on the, right-hand side, we have the any ref stuff. So this is actually most of your programs that you write are on that side of this thing, right? And on the bottom, we have null and nothing. So these are the common subclasses of every type. So everything, so nothing is a subclass of everything, basically. And on the null side, null is a subclass of the things on the right, of the anyref stuff. I'll show you an example of kind of when that's important. Scala has the ability to sort of prevent nulls from getting into different places. This bottom type here helps that, and there are other things like options and stuff like this that can prevent nulls from getting around all over the place. So next, how do you define some kind of thing that's eventually, type checked? So there's two ways. So declarations of named types, so via things like traits or classes or objects, these things are types. So you define a class or a trait, or you define a type member using the type keyword. So here is just a simple class definition. Animal has a field age int in the constructor, and then you have this thing here. The other one is this is the type member. So this is actually, it's a member of the class. So similar to like how a field or a method is a member of a class, but it's actually a type. So that's a type member, and then you have classes and traits and things like this. The other way is via combining things. So you can, so first of all, on the top side, this stuff is named types. Some types can also not be named. So things like refinement types or compound types. This is an example of a type where, basically I want to pass something into this obj thing, or I'm sorry, into this clone and reset thing that can both clone and reset. So this is basically a compound type, right? So these are the ways that you create types in the Scala universe. But I think what's most interesting is kind of when these things start getting richer, when you start adding type parameters to them. So what are parameterized types? So the same as generic types in Java. And a generic type is a generic class or interface that is parameterized over types. So basically, this class here is parameterized on some type T, so stack of T, and then there's some fields and methods here. And so T is the type parameter, right? And so I think what's actually interesting about these things is that you can kind of interact with type checking by adding or relaxing constraints on these parameters. So you can kind of control how the type checker behaves based on so-called constraints. And there's two kinds. So there are variants. So you can add, you can basically add, you can do this by variance or with type bounds. So who feels comfortable with these things? Because I think a lot of people kind of tend to be confounded by them. Comfortable? Okay, comfortable. Like it's okay. You're fine with it. It's not surprising. I know these names, but I mean, every time I'm in a situation, I don't know which one to choose, or I forget it. I try to avoid it. Anybody on that side? So, anybody? Do you guys use types at all? Like, okay. I can't get a read on you guys, but okay. So let's start with bounds. I think bounds are simpler to kind of wrap your mind around. So both type parameters and type members can have these so-called type bounds. So you can have lower and upper bounds, so subtype and supertype. So subtype bounds or supertype restrictions. On the one side, we have this example here with this box thing. So basically, box has some type parameter T that is upper bounded by tool, whatever tool is. So box can contain an element which is a subtype of tool, basically. That makes sense, right? That's kind of clear. Everyone's okay with that, I'm sure. There's all the other stuff that can be cool about this. So in this case, you can actually, this is maybe not the coolest thing to do, but the type checker helps you here, which is why it's cool, okay? So basically you can use null as in the type signature to say that something is allowed to be null in this class, right? So you can, so basically null can be used as this bottom type for any value that is nullable. And actually what's interesting, so I showed you this type hierarchy a few slides ago. Recall that null thing in the hierarchy. So basically it's the type of the null reference. So it's in the subclass of every reference class, so the things on the right of the hierarchy. But note that it's not value classes. So null is not compatible with value types because it's not on that side of the hierarchy, right? So basically that means that if you try to, this is really cool, look, if you try to say val I int equals null, then you get a type error. That's cool, isn't it? I like that. Okay, so variance is the other thing that people tend to be often confused by, I think more than bounds. So what is variance? Let's start with a little example. Let's say we have some container thing, aptly named box. And there are some stuff that maybe you want to put in the box, tool or hammer. So you've got a class tool and a class hammer, which is an extends tool, so it's a subtype of tool. And you might ask, okay, well, how do these things relate to one another? So we do know, so there's three possibilities that you can use a variance annotation for. So we do know this is always true. So we have covariance, contravariance, and invariance. And on the left side, these things are always true. So we know that hammer is a subtype of tool, right? But basically, this relationship can swap and go different ways depending on the variance parameter that you use, or the variance annotation that you use. So this is the most natural thing. So if I have a box of tools, then basically a box of hammers should be a subtype of that because hammer is a subtype of tools, right? That's sort of generally what you expect. You can have the opposite of that, and I'll show you a little example where that's actually useful. So you can have, again, hammer is a subtype of tools, but you can have a box where tools is a subtype box of tools is a subtype, box of tools is a subtype of box of hammers, yes. And then you can have the situation where there's absolutely no relationship at all. So you might write some program where you think that hammer, certainly hammer is a subtype of tools, so a box of each, I should be able to pass these things back and forth, and it won't work because you have to say that I expect this container type to have this container type to be contravariant or covariant or something else. And in the case of something that doesn't have so a class like box of T here, which doesn't have a variance annotation, this is by default invariant. So in this case, oh shoot, I didn't show, whoa, what did I do? I didn't show the actual code snippet. So in the covariant case, it's the same, box plus T. In the contravariant case, it's box minus T. And in the variant case, it's exactly the signature that you see there. There's an example, you'll see this if it's not clear. But let's start with covariance. So let's start with a cute little example, simple zoo-inspired example. We all love animals, right? So let's assume we have a trait animal, a class mammal, which extends animal, and a zebra, which extends mammal. So let's say we'd like to define a field for our animals to run around and live on, and we'll call that field. And it's parameterized by the animal that should live on it, okay? So let's define some function that can give us a Boolean answer whether or not the field is large enough for the sort of animal that we put on it. So in this case, let's maybe focus on mammal, right? And say let's let any mammal that we pass to it. So there's zebra. Maybe there's another subtype of mammal. Let's see if this function should, whatever it does, it should just test to see if the field is large enough for that mammal, right? So you write this function. It looks like this. Oh, sorry, this is called field. And it should return a Boolean. So given this abstract class here, how we define it, do you think that it's possible for a zebra to be passed to this function? Zebra's a mammal, makes sense, right? But no, it doesn't work because this field thing on the other slide was invariant. It didn't have this little plus sign here, right? I just told you about covariance. So a field of zebra is not a subtype of a field of mammal, even though zebra is a subtype of mammal, right? Because I said I only defined the relationship between the zebra and the mammal, but I didn't define the relationship between the thing that contains the zebra and a mammal. So in this case, in order to fix this and make it compile, all I got to do is add a variance annotation here, so make this thing covariant, and it compiles. So the same happens for contravariance. So let's imagine a scenario where we want to still run our zoo. Let's say that our zoo has several vets, and some are specialized for specific species. So let's say we need one vet to treat all the animals of our zoo. So this is what a vet looks like. It's just, again, the same deal. Method is called treat. So the vet's going to treat animals, and we assume we're going to pass an animal to the vet, right? So we want to define a method called treat mammals, right? And we want to pass a vet to it, and we want to parameterize it on mammal, right? So can we pass a vet of animals to treat mammals? So can we pass a vet of animals to this function? Because, well, mammal is a subtype of animal. I don't know. Mammal is an animal. So if you have a vet that can treat animals, it should be okay to pass a mammal, right? Again, no. You need a variance annotation to say that you're allowing the inverse relationship to be passed into this container thing. So it doesn't work because vet of animal is not a subtype of vet of mammal. The container, again, is not a subtype of one another. So despite the fact that mammal is a subtype of animal. So we want, so in general, we want vet of A to be a subtype of vet of B in the situation where B is a subtype of A. So it's really horrible in English to say that, but this picture really is much nicer to try and remember this relationship. Okay. So now now to the question: what's the difference between bounds and these variance annotations? So in the case of, like, yeah? Did somebody say something or no? Okay. So in the case of A being bounded by B, so A has an upper bound B. So A is a subtype of B, and B, is in a covariant position. So they seem kind of similar because they both have like this up arrow in this picture, right? Oops. So they're so you have this thing going on here, and then you have this. You can define some method where you say you allow box of tools, right? And then you can accept hammers and stuff, right? So there's a difference. So the symbolic version of this is to say that if you have a container, so in this case call, where A is a subtype of B or A is upper bounded by B, then it means that this call thing can take any class of A that is a subclass of B. So again, it's the relationship between these container things. Whereas, I'm sorry, no, the other way around. So it's what that container is allowed to accept. And in this case, it's the relationship between these container things. So call with the covariant type parameter means that call can take any class, but if A is a subclass of B, then call A is considered to be a subclass of call B. So this is the relationship between the containers, and this is the relationship between things that you can pass to one of these containers, right? So you can ask, well, okay, this is like all abstract, but why is it useful? So in the first case, it's useful when you want to be generic but require a certain set of methods in something like B. And then in this case, it's useful when you want to make collections, basically, and you want them all to have the same sort of behavior. So those are sort of the use cases for these things. And again, that was a little bit abstract, so maybe we can go back to our animal examples. So let's say we have a class animal and a class dog, which extends animal, and then also car and a sports car, which extends car. If we focus on the variant situation again, so we have, let's just assume that this isn't the standard library list. This is just list. It has it's covariant, and let's just say now we want to pass some things to this list. So if I say I have a list of animal and a list of cars, then I can pass, a dog, another animal, and to the animal list, and I can pass car or a sports car to the car list, right? So in this situation, as you can see, the list doesn't care whether or not it contains animals or cars. Like list doesn't care. List contains things, period, that have a relationship. Or basically, yeah, list contains this is between collections or between this container type. It doesn't care about the thing that's inside of the container. So the developer of list didn't enforce that, for example, only cars can go inside of lists. Whereas in the other case with bounds, that is the case. So here we have a type bound on this thing called barn. So we have the same animal and car classes that we've defined above, and so we add a bound on the type parameter to barn. We bound it so we have an upper bound on animal, right? So that means we're going to pass an animal to the barn. So then if you try, for example, to pass a car to the thing that expects an animal, then of course you get a compile error. It says the inferred type is sports car. It doesn't conform to the applies type parameter bounds, which is, animal. So clearly a car is not an animal. So as you can see, barn is a collection intended only for animals and not cars. Does that make sense? That's, I think, more intuitive than this jargon thing. I just hope to show these cute little examples of kind of the differences between these things, because I think very often in conversations, if you're reading the mailing list or something, you have all kinds of, well, this is in a contravariant position and that thing is invariant, blah, 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 and you don't have maybe a visual picture of how these things work. So I hope that this made it a little clearer. But okay, if you write code in Java all the time, and maybe you might know that a lot of these things kind of exist in some way or another in Java. They don't look exactly the same, they don't have the same names, but they're basically the same, some of them. So what kind of stuff exists in Scala that's useful that doesn't exist in languages like Java? So this is where things like these abstract type members or type members in general come in. So I showed you a little bit earlier, there's this like type keyword, and you can make a member of a class or a trait, and you can say, I don't know, type dog, and you can put it inside of something, right? So that is an abstract type member, because I just say type dog. I don't say type dog equals, I don't know, something else. So actually, why would I care about this? Why is it something that I claim is useful? It turns out that it's actually a pretty powerful way of abstracting over stuff. And actually, Martin once wrote a paper with Phil Wadler and Kim Bruce, I think in 1998 or so, where he basically tried to show that you could do parameterization with type members, basically. And he found that actually it's a little bit more concise to do it this way, because something happens, I'll show you in a second, when you use type parameters instead of type members, you could end up with a signature that gets to be ginormous, where you're parameterizing all kinds of stuff on types. You're carrying it around each time you extend that thing. So anyway, I'll show you that in a second, but the fundamental idea of that I want to express to you is that a type member is a thing, or especially an abstract type member is a thing where you can define a type inside of a class or a trait or whatever, and you leave it abstract until you know what the type in it should be when you need to make it concrete in a subclass. So it's very much like a type parameter. You make things concrete as you go down when you have a trait at the top of a hierarchy somewhere. So here, let's look at an example, keeping in mind this idea. So given, again, I guess I like animals today, I don't know. Let's say we have a pet, and we have a cat, which is, extends pet, the type of a pet. Let's create a person who has a cat, and let's create this person equivalently, so with type members and with type parameters. Does anybody know how to do that actually? Is this obvious? So if I want to say I have a person, and she has a cat, but I want to parameterize this, have a type parameter or somehow do this with types. And do it like this. So these two things are equivalent. So if I have this class person, I create an abstract type member pet in the abstract type members case. And then when I want to create Susan, I extend person, and then I make pet concrete. We created cat there, so we know cat exists. So basically, the pet that Susan has is of type cat. This sounds so silly saying it out loud, but I mean, do you, I don't know, have some intuition, or can you visualize this? It's the same as what you kind of always do with type parameters, where you say, okay, I have a class person, I parameterize it on pet. Okay, now I create Susan, I extend person, and then I have to make this concrete in the subclass, right? So notice, well, actually, here, I'll show you in a second when this can get a little bit verbose. So this comes from, this is an example that comes from one of Bill Venner's blogs. And so he was basically trying to figure this out because, you know, Martin made some cryptic comment at some point saying that yes, it can be more elegant, and Bill was like, well, okay, why? I don't get it. So what he tried to do was he tried to allow users to write tests into which they could pass this thing called a fixture object. Who cares what it is? If you know Scala test, great. But if not, it doesn't matter, it's just the name of it. So in this case, f would be the type parameter. So let's just look at the top one for now. I mean, actually in both this is true, but the type parameter in the top one, this f thing, this is the fixture that you would be passing into the tests, which then subclasses would eventually make concrete. So this next thing, this string builder fixture thing, is a certain kind of fixture, right? So one that you know, deals with strings. And if you don't know what this thing is here, it's a self-type. And basically, we don't need to get into it really right now, but the end result of that thing is all it does is, so this is a string builder fixture. It's a trait. This self-type makes it so that I cannot mix string builder fixture into a dog or a pet or something else. I can only mix it into a fixture suite string builder thing. So I can only mix it into that type. That's all that means. So I'm restricted on what I can mix it in with, right? So now this my suite thing is what a user is expected to do. And if you notice, there's a little bit of a usability difference that happens at the user's level here. If you're the astute audience member will notice that we begin repeating the type parameter. So string builder it begins to repeat itself. Whereas in this case, we don't have to because we define it here, right? So as soon as a user tries to mix in the string builder fixture into a suite class, you see that you start repeating things. So the idea is that sometimes it can be more concise to use this, to use the abstract type member approach, and it achieves basically the same thing. And I think in the end, Scala test did this. So anyway, the takeaway from this is that abstract type members, abstract type members can give you abstraction capabilities without as much verbosity as type parameters, so it can be drier in some scenarios. Existential types. Anybody comfortable with them? Do you use them? I think everybody uses them, but nobody understands them. Is that it? Actually, they're difficult to explain as well. But I mean, you don't really need to know like the theory behind how they work. So actually, you're using existentials all the time, every time you have a little underscore. But basically, what this means is, you know, you want to, well, basically, you don't want to have to say what T is. You effectively want to get code to compile without, you know, like coupling in sort of what T really is. So basically, an existential type is a type where some part of it is unknown. So you know, an existential type includes references to abstract type or value members that we do know they exist, but we don't know what their concrete values actually are. So we know that they exist somewhere, but we don't care what they are. So in the example above, T is a type that we know, we don't know concretely, but we know that it exists. So the idea, like really the idea where it actually in the end ends up helping people or benefiting them somehow, is that it allows people to leave some parts of their program unknown, and the thing can still type check with different implementations for those unknown parts. Does that make some kind of sense? So here's a little example. This doesn't do anything at all, but it compiles. Can somebody tell me what T is? Does anybody? Nobody cares what T is, because the whole point is that you know that it's an existential type and we don't care. So yeah, here we are. Sorry. So this type T, it doesn't really matter what it is, but we know that it exists, and you know it's a part of fruit, right? So I have another cute little example where we can make code that should compile using existential types. So let's first start with this method, foo, We want to pass to it an array of any, and then we try to pass to it, an array of strings. That doesn't compile, because an array of string is not an array of any. However, it's type safe, because we don't really care about the type inside of it. We know that we're just calling x.length. X is an array. So if there's an array of strings or an array of integers or an array of whatever, you can still call length on it. So that code actually, makes sense. But it was rejected by the compiler. So how do we fix it? We don't have to use existential types. We can use type parameters to fix it. So we can just make a foo parameterized on some type t, and everything works. And you get the length of this array. But actually, that's unnecessary. So just to make it compile, we have to have a type parameter, but we don't care what that type parameter is, because I just want to know how many elements are in an array. I don't care what they are. So the type parameter isn't necessary. Maybe we can do better, and of course the answer is that we can use existentials to get around this. So we do exactly the same thing. Instead of having a type parameter on foo, we just make the type of this array of t for some type t. Like, we don't care what that type t is, and this thing compiles. And it works, and it's great. So if I have a much larger program, I don't have to be worrying about making sure that type parameters are all over the place in my program, right? Okay. Oh yeah, and again, I want to point out that you're using them all the time. It's this underscore thing. These are existential types. This is the longhand version of them. Oh, and I found a really nice quote by Burak Amir, who was the guy who wrote the first pattern matcher on Scala. And I found it, I'm just going to read it because it's quite nice. So why these things exist, they provide a way of abstracting type information such that A, the provider, the thing that's providing this thing, can hide a concrete type and thus avoid any possibility of the client depending on it. So you're never leaking that information out to the client. And a client can manipulate the said type by only giving it a name and then making use of its bounds. They can't be doing other things with it. So it's just an information hiding thing. Existentials play a big role in our understanding of abstract data types and encapsulation. It's true. But anyway, all you really got to walk away with is the idea that, okay, existential types let you decouple implementation details from the types. That's why they're useful. And the last thing that I really want to go into detail about is our type classes. So type classes are not a feature of the type system, because in Scala they're a pattern. So you bring together other things that are in the language to create, to simulate basically type classes. So it's called the type class pattern, we call it usually. Other languages like Haskell, it's built into the language. Okay, but what type classes do? So type classes are useful. They're very useful in my opinion. They enable retroactive extension, so the ability to extend existing software modules without needing to refactor or recompile the original source codes. So this type classes are a mechanism to allow for a disciplined alternative to ad hoc polymorphism. So on the high level, a type class is simply an interface that provides operations over one or more generic types. Can people think of an example where type classes could be useful? A situation where you want to provide some functionality over like bazillions of different types that could be very different. Yeah, but also pretty printing, things like this. If you want to string something, you print it in a way that's nice, right? So you want to do this with basically all of the types. And each one maybe has a different way of doing it, like serialization. So if I have a person object, it's serialized differently than an int. So you need the implementation to change, whereas you know always that you're going to have a serializer of type whatever, person or something else. So they always have a pickle method, for example. So speaking of serialization, I'm using serialization as an example. So let's talk about how I can make a type class exist, period. So a type class comes in two parts. The first part, is the actual, well, it's the interface, but this is the actual type class itself. So the first part is the interface that says what should be implemented. So in this case, we know that we want to have a type class-based serialization library. So we know that we need picklers, and we know that we need them for every type T that we have in our library. And in order to serialize an arbitrary type T, I need to implement this pickle method. Right? And the pickle method takes an instance of T and returns, in this case, an array of bytes. So we know that that's the interface that should always work that way. But we need it for all these different types that may potentially exist in my library. So it could be hundreds. So in this case, then, there needs to be a pickle method provided for every possible type T. And those are the type class instances. So this is the type class, and this is the type class instance, so the actual implementation of it. So in this case, it doesn't really matter how it's implemented. Let's just say that I've implemented an int pickler. It extends a pickler of type int. So I've made the type parameter concrete. So it was T, now it's int, right? And then I say, OK, I have an instance of int, and this is how I take an int and make an array of bytes, right? And I have this implemented as an object. However, the issue here, so it's not quite a type class yet, because all of this stuff kind of has to happen automatically. So this is when this implicit keyword comes in that does all of the automagical wiring. So basically what this does is if I create, so without this, every time I would need an int pickler, I would have to use this by name. I couldn't use the type anymore. I couldn't say that, I want a pickler of type int, in this method here. I would have to actually remember the name and call it, which is, maybe not so easy if I want to start composing these things. So if I want to use the int pickler inside of something else to pickle one of its fields, for example, this gets unwieldy. It can be done automatically with implicits in Scala. So what this does, this implicit keyword, what it does is it looks in what's called implicit scope for something of this type. And if there's something of this type existing, then basically the compiler just rewrites things so that it gets called. So all you got to do then, as a user, is make sure this thing is in the same scope as where you want to use it, basically. And and then I'll show you actually how to use it now. So here's an example of how you should use one of these things. So let's just say now I have a library with many possible T's, and I want to write a method called persist. And as a part of that method, I need to serialize stuff. So that method takes an object of type T. It also takes this funny extra parameter list here, this implicit pickler of type T. We'll see what that does in a second. But assuming that I have this thing called P that has that type pickler, then all I got to do, well, I should be calling pickle on the pickler, but yes. So, oh yeah, and this can be shortened, by the way. So basically what this does is this looks in implicit scope for that other thing that I said should be an implicit scope. So if we go back to the previous slide, if I define this thing in the same scope, then this is floating around in implicit scope, and it has this type. And so when I try to compile this piece of code here, what happens is this thing, implicit, and it looks around in implicit scope for that thing of type pickler of whatever, wherever it ends up being actually used. So in this situation, I can use it here to call persist on 15. And because I know the type of 15, it's an integer, it causes that whole chain of reactions to happen, where this method demands an implicit pickler of type int, and then the compiler makes sure that it's in scope. So this is no boilerplate. I can just say persist on a number, or persist on a string, or persist on anything that I have implemented a pickler for. So if I have one of these in scope for the right type, then it should should always be wired up correctly. I just call a method, you know, that maybe requires that thing, right? And that's it. I don't know if that was complicated. Everybody tries to explain type classes to varying degrees of success. But yeah, I hope that explained it. So really, again, if there's a takeaway here, oh yeah, the idea is that you can retroactively add functionality without having to recompile. So in this case, I can just throw in, like I can just import somebody else's separately compiled picklers somewhere else. I don't have to change my code and recompile stuff to provide that functionality, which is the benefit, really. But that actually does it for my list, and I'm at my time limit already. But there's of course a lot more. So these are the things. So in my opinion, if you understand these concepts and you put them to use in your programs, or you see somebody else writing code where they make use of these things, these are the uncomfortable, confusing things that normal people do. I don't think that any of you should be digging around in the internals of some of these libraries that do all of this generic deriving of type class instances. That stuff is ridiculously complicated. I'm not suggesting that you should try to go down that chute and learn all that stuff. Instead, really, the things that I showed you so far are really, in my opinion, the max that you need to know about to make effective use of Scala's type system. You don't have to know all of the ins and outs of things like path-dependent types. Or, you know, you can do really cool stuff with path-dependent types, but I don't think that everybody should be. It's not necessary. You can do these things often in other ways. So in my experience, basically, I think that sort of the other advanced stuff, so like these tricks with dependent types, even higher kind of types sometimes, or a lot of this type level programming, I think this stuff is advanced, and I don't think people need to know this to be actually very good Scala programmers. So I think you know, by just understanding very well how to make use of these bounds and variance annotations, and if you figure out how to make type classes work for you, I think that that's really, like, you know, the most that you'll ever end up kind of coming across, unless you start getting into some of this more advanced stuff. But if you're interested, nonetheless, I encourage you. There's not, I mean, there's a lot of people giving talks about this sort of stuff, and so there's not, I mean, people are basically figuring a lot of cool things that they can do out. So, but written down, if you want to go look at it now, there are two places where you might be able to learn about some cool type system tricks. Actually, Konrad Malowski, so he works at Lightbend. He has a wiki of type system constructs and other sort of patterns with the type system. Some of them are supported, some of them are accidents, but he's trying to make an entire list of everything that exists. And then, of course, the type level folks have really an amazing blog about some of the stuff that they make use of. So for example, they have a really nice blog article about existentials and you know, why they are much better than using raw Java types or Java raw types, whatever you want to call them. And I just wanted to show real quick. Oh no, I think I have. Do I have Wi-Fi? Awesome. Okay. I wanted to show this is Conrad's dictionary here. Oops. Hold on. Okay, this is his little encyclopedia of types. Some of them, I mean, some of them are, you know, not really their own types, but they're basically everything you could ever ask about a type or anything that you might ever come across. So, I mean, you might hear all over the place the word type description. This is basically just, you know, like saying what the type is of something so that the type inferencer doesn't have to, you know, like try to figure it out. Things like this. So he goes through basically everything that exists, and like I said, there aren't 29 or 28 kinds of types. It's just everything that you ever might come across is here, even though it's not really like individual type system features. But that's it. I have a thank you slide. If anybody has questions, I'm happy to answer anything. I also have stickers, by the way, if anybody wants one.
Can type members have bounds and
Yep,
variance?
good question, yes. So one thing I didn't do is show you how these things interact. But yeah, so earlier, if I go, wait, oh no. It's impossible to see this now. Yes, I did it, okay. So if we go back to these examples of type parameterization, right? So here I'm saying that I can make this type parameter basically happen with abstract type members instead. I can also, you could imagine that I bound this on something. So pet is a subtype of, I don't know, whatever animal. I can do the same thing here. So I put a bound as well on the type member. So yes. Yep.
Is it the same mechanism like plus minus?
Oh, the variance thing?
For members versus representation?
Oh, no. No, it's a good question. No. Because remember, it's like a container type thing.
But you'd have to get the full type.
Yeah, so you can put bounds on these, on abstract type members, but not variance annotations that I know of.
On your question on your example on type classes, was there a reason that we had to give a name to the pickler, even though we never use it by name?
Well, because you're creating, I mean, actually, you have to because it's an object and it's a nominal thing. But yeah, you're right. Since it's always going to be implicit and whatever, and we only care about the type, you should never, well, actually, yes. In your head, no, but somehow the type checker needs to rewrite things so that thing gets called. So yes, of course, because basically all that implicit search does is it rewrites things, or rather the type checker, when it goes into implicit search, it just rewrites. So it rewrites like this call that you have where you just, like, it rewrites that thing with the persist to actually use the named thing. So yes. I guess, yeah, but try not to. Anybody got any other questions? Anybody want a sticker? Okay, come get stickers, I'm done. Woo, thank you.